Okay, so this is the second video for comparing two proportions. In the first video, we did a confidence interval. We're going to do one more confidence interval, and then we're going to talk about what pooling means and figure out how to run a hypothesis test with this. Okay, so you're going to probably have to write this one down if you did not get the little piece of paper. This is a new problem. So a recent study asked 131 women and 61 men, would you date someone with a great personality even though you did not find them attractive? 61% of women said yes, while only 43% of men said yes. Assume all conditions are met, and we're going to skip to finding and interpreting the 96% confidence interval. And so we're skipping because it's the interpretation and the finding that I want to make sure that we're able to do. Okay, so we're still going to say what it is. This is a hold on. So this is a difference of proportions, Z interval. That might be a little too thick, hold on. And we have our P of men is 0.43, our Q of men is 0.57, and our N of men is 61. And then we have our P of women, which is 0.61, our Q of women, 0.39, and our N of women, 131. Now, you might say, hey, the samples weren't the same size. I mean, one's double, but it is okay. That's not going to cause any issues because 61 is still a large enough sample. Okay, so we can go ahead and proceed. It won't be a big deal. All right, so now we need to find our SE. And so we'll do 43.57 divided by 61. Okay, and so I found, when I did all that, I got 0.076. I'm not going to round that to 0.08. I'm going to keep it there. And so our mean that we use, we're going to subtract our two P's. And so 61 minus 43 is 18. And so we're going to use 18, and then we use our 0.076. Okay? And so now with a 96% confidence interval, remember, some of you are really good, some of you are still struggling with this or can't remember all the time. If 96% is in the middle, that means there's 4% on both sides, so it's 0.02. So I'm going to do my second vars and do my inverse norm of 0.02. And so I got negative 2.05, so I just ignore that negative. Okay, so now what we're going to do is we're going to find our confidence interval. I'm going to use our mean right here. So 0.118 plus and minus the 2.05. You like that marker? It kind of changes. It's awesome. Times the 0.076. And so when I do that plus and minus, I'm going to get this. Okay, and so what I get is I get 0.0242 to 0.3358. This problem is different than this one we had above. This one we had above had a negative, so that means sometimes one group was higher and sometimes the other group was higher. This one is all positive, meaning women are always higher. And so the way that we're going to do this, well, let me make this bigger so you can see it. We know that women are always higher, so we are 96% confident that the percentage of women that say they would date someone for a good personality is between 2.4% and 33.6% higher than what men said yes. And so we don't have to say higher or lower because we know it is always higher because it's always positive. Okay? So most of your answers are going to only have a positive range, meaning there was a difference between the two. This problem from the day before, from the lesson before, it was negative. So sometimes women were higher, sometimes men were higher. So when you have them when it's always positive, then you know that one group is always positive and there's always a difference. They're always higher. Okay, so now what we're going to do is we are going to do our pooling. And pooling is something that you don't do that often. And when you pool versus not pool, it actually doesn't make much of a difference. But for AP Stats, you definitely have to be able to identify when you would pool. Okay, so pooling, what we do is we're going to combine our counts to get a more accurate proportion. The reason you pool is if you think they came from the same population. If you think two groups came from the same population. So if you think that they're actually pulled from the same sample, same area, that's when we're going to pool. So to find the equation for how we actually pool, what you do is you're going to combine your successes of the first group plus your successes of the second group, and then you divide that by N1 plus N2. And so that's your new pooled. Okay? And then it's the same idea for the Q's. And so when you end up with your standard error formula, it's P pooled, Q pooled over N1. And then it's that exact same thing right here over N2. So the biggest work is actually finding your pooled percents first, and then you multiply them on the top of both things. Okay? You will not pool that often, but occasionally you will, so you have to recognize it and you have to be able to use this equation. All right, so the last thing we have for notes part before we go back to our examples is the 2-prop z-test. Okay, so you know how to run a 1-prop z-test. You know how to check conditions. Let's see if I can find them. Yeah, buddy. You know how to check conditions for interval. So you have to check the conditions the same way. So check conditions for both sets, both groups, like we did above. You have to list your parameters for both groups. And then you have to do your ho and ha, which we have above. Your ho, your ha, right? And remember up above, we took this the other day, you have to set them either greater than, like 1 is greater than, they're less than, or not equal to. And we always do the big minus the small, okay? And then you run your test and you find so what will happen is when you draw your normal model, when you do your mechanics, what you'll set is, remember your ho is always what your mean is. And so all of our ho's are 0. There's no change there's no difference between the groups. But you draw your line, what the actual difference was from the groups, what you found. Okay? And then you either reject or fail to reject the same way we did before. Small p-values get rejected. Large p-values we fail to reject. Okay? And so let's go down and do a problem. And we could actually look back at this problem right here, this presidential problem, right? We did not write the ho and ha, but we can let's just add the abbreviation to it so you have just another example. So I will use purple. I didn't use blue. I use purple a little bit. We'll use green. Okay, so the ho is that there's no difference between men and women. And so it would be, which one was higher? Men. The probability of men minus probability of women is equal to 0. And then the ha, it said for the difference between. And so it did not say whether one was greater or less than. It just said there was a difference. Let's see, well, maybe. Oh, see right here, it says he has a problem with women. And so we're saying that men is higher. And so then that would mean that we would subtract and be greater than 0. So if men is higher, then we would subtract and get greater than 0. I'm not going to do the rest of this problem because we actually already have the answer. Right down here when we found our confidence interval that made this problem so tricky, You know how sometimes women were higher? Since 0 is in this interval, it's a fail to reject. There's not enough evidence. So if we were using this for height test, right there, because 0 is in interval, we fail to reject. Because sometimes women were higher. And so we are not going to get a super small p-value. We're going to get a medium-sized p-value. So sometimes you can reject or fail to reject from confidence intervals too. Okay, so then let's look at this next one, the part B problem that we just did. We said it says to find and interpret the confidence level. So we don't know the ho and the ha. It doesn't say higher or lower, so it would just be a change. But you see this? You see how 0 is not in here? They're between those two. Women are always higher. So that means there is a difference. And so this one we would reject the null. There is evidence that women are always higher. Okay. All right, so let's actually do a full test here. Let's talk about it, and then we'll pause, and I'll write a bunch of stuff, and then you can check it. So researchers identified 450 people with cardiac disease, evaluated them for depression, then followed the group for 4 years. Of the 361 patients without depression, 67 died. So let's see, probability no depression, 67 out of 361. So that means the Q of no depression, we'll have to do some math real quick. 361 minus 67 is 294 out of 361. And the N of no depression is 361. And then of the 89 patients with depression, 26 died out of 89. And then so that leaves 63 did not die. And the total N of depression was 89. Okay. Now, when you look at this, researchers identified 450 people with cardiac disease. This one is actually going to be, let's see if this one's going to be pulled. Hold on. So for this one, we're actually going to pull this one because they had to have that same population of having cardiac disease. And so they came from the same group, and then they split them up to 2 with depression, without depression. So this is going to be pooled. Okay, so I add my 67 and 26. Those are my 2 successes. And success happens to be dying. And that's 90 out of 450 because it's the whole sample. And then the ones that didn't die are going to be everybody else. So that's going to be 360 out of 450. So these are the numbers that I have to use when we do our standard error. Okay, so let's go ahead and do our ho and our ha. And I'm going to type those so that you can read them a little better. Why don't you go ahead and try it, and then you can press play when you think you have it. Okay, so we always start with saying there is no difference. So for my ho, I said there's no difference in death rate for cardiac patients with and without depression. And so I couldn't type this, but it's going to be P with depression because that's the one that they're saying is more, minus P no depression is equal to 0. And then this one, it says they're more likely to. And so P depression minus P non-depression, that's going to be greater than 0. Okay. And so now we have our conditions. We have our parameters. We don't have our conditions. We have our ho and our ha. We have our parameters. We should say that this is a difference of 2 props. Z test. We're doing a test. Okay. And now we need to check our conditions. So go ahead and try and check your conditions and then press play. I'm going to type them again so it's more legible for you. Okay, so here's our conditions. We can assume both samples are representative. It doesn't actually say it was random, so we have to say that we assume that they're representative of the population. Death is independent for each group. They're both less than 10%, and then I showed that there was both 10 successes and 10 failures. And remember, success is dying, and that sucks. There is one thing that I forgot to mention. It's not just a 2 proportion, it's a pool. And you just have to say somewhere that you're pooled. Okay. All right, so now we know our mean is going to be 0, comma something, and that something is where we're going to have to do our formula. And so it's going to be helpful if we figure out what these percents right here are. So 90 divided by 450, this is 0.20. That makes it easier. That's 0.80, okay? And so now we're going to use our formula to figure this out. Okay, so scroll up. We do need to make sure we can see those ends still. Where are they at? Okay, so it'll be the square root of 0.20 times 0.80 divided by our first sample, which was 361. And then we do the same pooled 0.2 and 0.80, and now divided by our second sample, which is 89. And so you do all the hard work up above, and then we just have to use those percents. So let's see what we get. So I got 0.047. Hopefully I did it right. Okay. And so now what we're going to do is we're going to draw our line. And we have 0 here. And now we have to figure out what the actual difference was. So we have to figure out what these were. What's the difference of that? And so it's going to be helpful if we first find out each of those proportions. So 67 divided by 361, that's 0.186. So 0.186. And then the next one, 26 divided by 89, that's 0.292. Okay, and so we have to subtract those two numbers right there. So 0.292 minus 0.186 is 0.10. So that looks like a really big difference. So let's see if that's large enough to show statistically that it wouldn't happen. And so the difference, again, was the 0.292 minus 0.106, and we're going to use 0.185. Sorry, I wrote the wrong number. So the difference is 0.107. Okay, and it's above, so it's shade to the right. And look, this is also above, so it's shade to the right. So now you're going to use your calculator, and you're going to do normal CDF with 0 and 0.047 and find out what percent of the time it's shaded 0.107 or above. I don't have my calculator today, so I'm hoping that I did it right. I had to use an online resource, and I got what did it say? 0.0114. 0114. So hopefully we got the same thing. If we didn't, I apologize. There's no way for me to double check. And so that's a small p-value. So now we know that we can reject. So with a small p-value of 0.0114, we can reject the null. There is strong evidence of a difference of death rate between cardiac patients that suffer from depression. They die at a higher rate. And so here, because they die at a higher rate, the next question they might ask you is find that rate. And that's when we would just go to a confidence interval. But today we're not going to do that. We have our conclusion. We have a small p-value, so we know we can reject. There's strong evidence that those patients that are depressed or have depression do die at a higher rate. Okay. So lots of little stuff, but stuff that you can do. Just follow the process and you should be okay.